Hello students, welcome to the class. Let me first talk about what we are going to learn in today's lesson. There are a number of objectives. As you are aware, the a system of linear equations can have three different possibilities when it comes to the number of solutions, right? No solution, a unique solution, or infinitely many solutions. Firstly, we will learn how to identify that based on the result of solving the equation. At the end of your process of solving, you will reach a conclusion, right? Based on that conclusion, how to know conclusion in the sense you will reach a final statement. I mean that you will reach a final statement in solving the equation. And based on that final statement, how to know how many solutions the system has. Okay, we will learn that. Then we will learn get a practice on. Okay, you have seen some examples in my the lecture video that you must have watched prior to this, where we talked about the method of using row operations to solve systems of linear equations, and we would have looked at an example. Here you will get more practice on that. Okay, on that method of using row operations. And then we will also try to get some conceptual clarity on the graphical and the analytic part of the equations. Okay, particularly how to look at equations and do some small manipulation and associate those equations with their graphs. Like here you can see if there are a bunch of graphs and equation, which one represents those. That will, when we try to connect them, some concepts will get clarified through that. Okay, that will be our goal. And then we will also look at there are a number of like practice problems on that, and then we will look at some practical real world problems also. Okay, we might solve maybe one of them. Okay, and as you can see in when I'm running through these pages, there are so many uh, uh, copies, I would say, of similar problems, and I will work through some of them. The rest I would want you to practice. Okay, let us begin. The first few eight, to be precise, the first eight questions are all of the same type. Okay, what they do is they say that you try to solve a system of equations and you arrived at this conclusion, this final statement. What does that mean in terms of solutions? Okay, and one more thing before we proceed. Although we will be interested in, of course, more than two variables in three variables also, especially when we use matrices to solve equations. The reason we are doing only two variables here is for keeping the problems themselves simple, but focusing on the concepts that we have to learn for the system of linear equations in general. Okay. Hmm. Let us start. If the addition or subtraction of two linear equations results in the equation 0 equals 2, then the graph of those equations are the same. Okay, how true is that? And the analytic part here is this part. You arrived at the situation 0 equals 2 at the end. That doesn't sound correct, right? And yes, whenever that happens in a mathematical sequence of logical statements, you say that you have reached a contradiction. Okay, contradiction is an obviously false statement like this 0 equals 2. And I started with a set of equations and I followed all the rules correctly. Okay, that is important. And I arrived at a obviously false statement. What does that imply about the original equations? Okay, that implies the original equation should not be possible, right? In the sense, what do I mean by that is the original equations have some inherent inconsistency inconsistency in them. Okay, so the another word here is inconsistency. The equations are inconsistent because when you try to solve, you reach a contradiction. Okay. Now, what is inconsistent? Two equations which tell impossible things. So, simple example, one equation tells you x plus y equals 5. The other equation tells you x plus y equals 7, suppose. And if you subtract these two equations, you will get exactly that 0 equals 2. Right? Now you think about this. How can x plus y be both 5 and 7? That cannot be possible, right? In such a case, obviously there is no solution. Okay, so all these three things, actually, these three that I put in quotes, contradiction, inconsistency, no solution, they are like synonymous in the context of solutions of linear equations. Okay, they go hand in hand. So there is no solution for this system. Now, all of these ideas we are associating with the graphs. Then will the graphs of those equations be the same? You'll obviously say false. If the graphs are same, you would have had all the solutions there. Alright, the graphs in fact will not intersect at all. The graphs will be two lines which will never meet. Because wherever the lines intersect, you have your solution in two variables. Okay. If the same thing was in three variables, it would have been two parallel planes, like the floor and the ceiling. Okay. In 3D space, if you imagine the floor and the ceiling, they are never going to meet. If you just look at the floor and ceiling, that would be represented by three variables. Okay. Two parallel planes. Okay. Moving on. The next question actually gives you the correct option. Okay. If the addition and subtraction gives you the result 0 equals -4. So something again contradictory, doesn't matter, no, the values, basically something fundamentally false. Then the graphs of those two equations are parallel. Yes, that is true. Okay. And there is a little bit more to the story, which is parallel and you should say and distinct. I mean, that doesn't make the statement false. They are parallel, that is true. But for full disclosure, you should say and distinct. Because if they are parallel and coinciding, there will be infinitely many solutions. Both the equations will be the same, the first case. Okay. Actually, if both equations are the same, then also you can say they are parallel in some default sense, right? If they're exactly the same, they are parallel. But they have to be parallel and apart, that is distinct. And where does that distinctness or not being the same comes from in equations? If you look at here the right side, x plus y is 5, will give you like the intercepts at 5 0 5 and 5 0. X plus y equals 7 will give you why just say, let me show you quickly. So x plus y equals 5 is, let's say, here. X plus y equals 7 will be here, right? That makes them parallel and distinct. Okay. In that case, there is no solution. If adding to linear equation gives x, now there different type of result is coming. You try to add the equations, the y variable cancels and you get x equals 5. You subtract the equations, the x variable cancels and you get y equals negative 5. So basically, you got a solution to the system. You have like x equals 5, y equals negative 5. That's an exact one solution, right? So what did we get here? We got a unique solution. Okay. Now, is the system consistent in the language of consistency and inconsistency? Yes. Okay. So it is consistent. It has a unique solution, exactly one solution. Think of the graphs. Okay. In the context of graphs, what would that mean? When would we have exactly one solution from graphs? The idea of the graphs is the solutions of the equations are where the graphs intersect. So if there is only one solution, that means the graph intersect at only one point. That is your solution. In fact, in your coordinate plane, if you had your x-axis and y-axis like that, that point here would be 5 minus 5. Okay. That should be in the fourth quadrant. You understand, okay? I'm not going to redraw. The point is, these two lines should be intersect. Okay. So the question here says they are parallel, and of course that is false, right? The next question gives you the correct way of expressing it. It gives you, suppose you add and subtract and you get x equals 8 and y equals 8. So that's one point, that would be in the first quadrant. Okay. I can do that correctly. Okay. And like that. So the lines must be intersecting over there. And that means the equations intersect in a single point. That is the correct option, A. Okay. So if you want quick clarity here, so the value of both x and y being equal is irrelevant. Okay. The point is there is a unique solution. That is the main concept here. If the addition or subtraction of two linear equation results in 2 equals to. Interesting. Okay. So again, unlike 4 and 5, where we had a specific value of x and y, we did not get that. Those variables got cancelled out again. Okay. But what you got was not some contradiction, but something that is always true but meaningless. Okay. 2 equals to. Right. So a number of things you can say here. The system is consistent as far as consistency is concerned. Okay. Because we don't get a contradiction. There is nothing wrong in saying 2 equals 2. All right. So if it is consistent, that means there should be some solutions, right? It's not a no solution situation. Solutions are there, but those solutions are not just one, infinitely many solutions. And why is that the case? Here is a way to understand why there should be infinitely many. Because if you arrive at the final statement, as a result of those equations, if you arrive at 2 equals 2, you are basically saying you give whatever x you want. This will always be true. The vectors, the variables are cancelled out, right? So no matter what value of x and y you give, they will be true, and you will end up in something like 2 equals 2. Okay, that's an that's a way of looking at it. And now, what would that mean in terms of graphs? The graphs, if they are having infinitely many solutions, they should be on top of each other, right? If this is one of the lines, remember the points on the lines are possible solutions. Okay. And if there is a second line and still you get all the same solutions, that means they should be overlapping on each other, right? Otherwise, the moment they are distinct, there would have been no solution. The moment they were not parallel, that would have been a unique solution. So what is the only other choice? For infinitely many solutions, they must overlap. Okay. So this particular statement, they intersect at a single point is false, of course. They must be overlapping, which I'm going to write here. Hmm. Coinciding graphs. Okay. In the language of graphs, we say they are coinciding. Overlapping is called coinciding. Okay. An example, I wanted to give an example for that, and I'm going to write a little above here. You had suppose x plus y equals 5 and x plus y equals 5. A very simple example. Okay. Two equations apparently, or oftentimes you will not see the same. You will see 2x plus 2y equals 10, say. Now, looks like they are different. Two equations, sorry. But if you look at the second equation and divide both sides by 2, you will get x plus y equals 5, the same equation, right? And when you do that and subtract x plus y equals 5 with x plus y equals 5, you will get 0 equals 0, right? Which is like getting 2 equals 2. Okay. All right. If the addition or subtraction results in something like 5 equals 5, then the graphs of those equations are the same. Okay. So the option B. Okay. So that was the clarity. In fact, we saw all three cases. Okay. Just to make it clear to you. We had like unique solution when the lines intersect, no solution when they are parallel and distinct, and infinitely many solutions when they coincide or when the graphs are the same. Okay. Um, the conclusions, that we got here as 0 equals 0 or 0 equals 2 or the value of x and y. Um, right now we are writing that, without matrices, but later when we do all of this with matrices, it will be the same ideas, but in the matrix form. Okay. And I will remind you or connect those dots back to you, back with this at that point. I'm just asking you to keep that in mind. Okay. All right. We will now look at solving some of these systems using the row operations we have studied. Okay. Find the solution to this system, and this question and all the subsequent questions, these instructions are the same. Okay. Like the three things, right? If there is a unique solution, write it as a pair. If there are no solutions, say inconsistent. And if there are infinitely many solutions, say redundant. Now, what would that mean? Okay, that is just a code word for now, just to identify that there are infinitely many solutions. But also it has meaning. Meaning is when you say redundant, as you saw here, you could say the second equation here is redundant, right? Because it is saying the same thing that the first equation is saying. Okay. So in that sense, there is redundancy in the system. In the system of linear equations, there are some equations which are not essential. You could have just skipped them if you knew better. That is the meaning. Okay. Because they don't provide anything new. They're just combinations of what are already there. Okay. All right. Let us now begin. You have this two equations. we'll use R1 and R2 to refer to the equations like rows, because row 1 and row 2, because that is how you will be dealing with them when you look at them as matrices, right? So let's get used to it. R1 and R2. So in order to solve the equation, what you would like to do is to eliminate, right? Eliminate a variable and try to see if you can, add or subtract the equations in such a way that you can eliminate. And all of this comes with practice. Okay, what exactly to do? The first step I would do here is I will simply do 4R1. First, in a few examples you see and try to understand what we do when. Okay. Why do I multiply by 4? Because that will make that 3y into 12y, which is what I am looking to cancel with the second row. That is the goal. Okay. But it also gives me 8x. See, when I decided on the operation, I was only looking at y. That is important. I was not looking at the entire row. I was only looking at the variable y and its coefficients. The second row has 12, the first row has 3. So I wanted to multiply the first row by 4 so that it will become 12. That's all. I didn't want to look at the x and the constant. That comes as a follow-up and it will have its own implications. Okay. Because when we do row operation, you cannot do multiply only the y variable. You have to multiply the whole row. So 12y minus 8x equals negative 8. Right? And let me simply copy the R2 below it. Just repeating it. Okay. And now what do I see? I see that the two equations are lining up perfectly. So what I do is subtraction in algebra. You can write them in operations as R2 or R1 minus R2. Who cares? It doesn't matter whichever way. You could do R2 minus R1 or R1 minus R2. Now, which R1? Be clear here, okay? And that is something I want you to again get used to. So right now when I say R1, this is my new R1, this row here. Because we are in this new stage. In this stage, that is my R1. I won't call it 4R1 anymore. Okay. That was 4R1 compared to the initial stage. We have moved in the current state. That is my R1. And R2, I have just carried over, you know, as it is. So in my current states, those are my R1 and R2. So I will deal with them. Okay. So when I do R1 minus R2 now, you get 0. Basically on the left side, everything gets cancelled. And on the right side, negative 8 minus 1 will be negative 9. Remember, we saw that earlier, getting a contradiction, right? That means the system is inconsistent. Okay. So another system here, but this time on top of like not just like answer options, but you are also given graphs. Okay. Let us see. Do a similar analysis, and now you know it. Okay. So I want to spend much time on this. If you multiply by 2, basically do the operation 2R1, you get 2x plus 16y equals 12. And you see that, the other row also has the same thing, but the right hand side is 14. So when you subtract, you are going to get the left side will be completely cancelled, but you will have 12 minus 14 on the right side. So 0 equals something non-zero, and you know the system is inconsistent. Okay. That's a second example for you. No solution, inconsistent. And also the graphical view now. Okay. Graphically, what is happening? Um, if you look at the second row, actually, you could let me also talk about that. one more operation. Okay. Or let me not erase them. I'll write here separately. Instead of that, you could do R2 divided by 2. You don't have to always modify R1. Okay. In the same original system, not new system. Suppose the first thing you did itself is R2 divided by 2. You will get x plus 8y equals 7. Because everything has a factor 2. That's easy. Actually, I should have done that first. Okay, that's easier. So you get x plus 8y equals 7. And you have your first row, which is x plus 8y equals 6. Now look at these two. X plus 8y equals 6 and x plus 8y equals 7. And that's what you are getting in your lines here. They have the same slope, right? But one is 6, one is 7. Two parallel lines. Okay. All right. Oh, I have to be careful here. Sorry. There are two of them. Okay, the graph should be like that parallel, but you have to look at the scale and make sure that you are matching the slope also. That is the second part of it. Okay. Um, let's actually do that, which makes me think that should not be the correct answer. What is the slope? The slope of this line, by the way, it's also a thing to review. If you rewrite that line, you get 8y equals negative x plus 6. So y is negative 1 over 8x plus 6 over 8, which will be 3 over 4. So the slope of the line is negative 1 over 8. Okay. In decimal, if that helps, sorry, in decimal, that will be negative 0.125 x plus 0.75. Okay, so I'm looking at my y-intercept to be 0.75 and the slope to be negative 0.125. So let us see. Here, the y-intercept doesn't match actually. You just check that. This one is better. Option D here. Okay, what do you see? The y-intercept is 0.75, between 0.7 and 0.8. And is my slope m negative 0.125. We can check that. How can you check that? The slope here is negative 0.75 divided by 6, right? This length is 6. Okay, and this height is 0.75. And this is, you can say this is negative 6 if you go from right to left. Hence, now when you divide, you get that, and you can check that is negative 0.125. So that checks out. Okay, your answer. Okay, parallel but also matching with the given data. There were more options given, but you understand. That's one more for you to practice. Okay, go ahead and do it. So I want you to think of them as rows and decide upon choose the row operation. What row operation will help you simplify? Okay, and did you do 2r1? That would have given you negative 2x plus 5y, because you can cancel them, right? Equals 18. What should I write that? Let me write here. If you did 2r1, you would have got that. And your r2 is exactly the same negative 2x plus 5y equals 18, negative 2x plus 5y equals 18. The equations are the same, right? Remember, that means infinitely many solutions are redundant, coinciding graphs. Okay. And there is more practice. Okay. I'll skip some steps here. Let us go to here, a variety. Okay. Now you have these two equations, x minus y equals 0 and x plus y equals 4. Okay. And think again, you can practice what row operations will you do. Okay. And you realize this time you don't have to do any multiplication. See, it's not necessary that you always have to multiply a row by something first thing. Okay. They are already given in such a nice way that only row operations you can do is R1 plus R2. Just add the two rows, right? Remember, that is one of the row operations. So when you do that, the y and y will cancel because you are adding them. You will get 2x equals 4. And then you solve it, you get x equals 2. Right? You can then do one of the two things. You can, this is called back substitution. You can plug in that, okay, in one of the equations and do this back substitution. Back substitution is you find the value of a variable, take it back and put it in one of the original equations. Okay. And if you do back substitution there, you'll get 2 plus y equals 4. And when you solve that, you get y is also equal to 2. Subtract 2 on the other side. And that's it. Then you have the value for solutions, unique solution, x equals to y equals to. Okay. That is one way you could solve it after finding x equals to, or after finding the x equals to, you could do something else also. Okay, what is something else you could do? You could do a separate row operation, which is you could do R1 minus R2. Now, here we did R1 plus R2 added, you could also subtract. And if you did that, x and x will cancel, you will get negative 2y equals negative 4. And then you divide on both sides by negative 2 and you get y equals 2. You will always arrive at the same answer, no matter what particular steps you follow. Okay. I showed you actually two different, a little different, I would say, methods here. In one method, after you find the value of one variable, you don't do the row operations anymore. You go with what is called back substitution. Okay. Choose one of the previous equations, plug in the value of that variable, and sometimes if there are more than two variables, like 3 or 4 variables, also you can do this, but in a number of steps. Now do one back substitution, it will give you the value of one more variable. Then now you have values of two variables. You go to one, a third equation and plug in both of them. It goes in that iteration. Okay, that is back substitution. The other method is, do some other row operations to eliminate another variable. Adding R1 and R2 eliminates Y. Subtracting R1 and R2 eliminates X. So you do like different row operations to eliminate different variables until you have a value for each of them individually. Okay. Okay. Keep all of this in mind when we do matrix version of these solutions later. It's going to be doing the same thing but in matrices. Okay. Coming to this particular question, our solution is x equals to y equals to. So here, x equals to y equals to the first option, but we have learned our lesson from past. We also have to check whether the equations make sense. If the equations are the same, not just the solution. Okay. The first one is x minus y equals to 0. Um, x minus y equals to 0 means y equals x. Okay, and that is this line. That is correct. The other equation was x plus y equals 4. And it has the slopes 0, 4 and 4, 0. And that's also correct. Okay, so that's your good. If you look at other graphs, 2 and minus 2, that's not matching. Negative 2 and 2, that's not matching. And here it has infinitely many solutions. The graphs are overlapping. That's also not the case. And here there are no solutions. That is also not the case. Okay. All right. And here are like more practice problems for you. Okay. Go through each of them and get enough practice, I would say. I'm just showing the questions to you. Okay. We will look at number 17, which has a little bit variety. Okay, so there should have been parentheses here which are missing. Sorry about that. I hopefully will upload a version for you where I do that correctly. Okay, and let us look at this problem. So in this question, you are given these two lines um, with those points, okay, passing through those points. And looks like they are all in first quadrant, so I'll draw it this way. And 0, 1, okay, that may be too much for 1. 0, 1, let's say here. And 1, 2, 3, 4, 5, if we do 4.6 might be somewhere here. 1, 2, say, 2, 3, 4, 5. 2 is somewhere there, 4.6 is there. So let's say the other point is somewhere here. So one of the lines would be this. Okay. And the other line is 2.44. 1, 2, 2.44. So approximately here. And 5.40. Okay, 5.40 will be somewhere here. Okay. And where they intersect will be our solution. That's the line. So one of the takeaways from this problem is when you're basically the systems of linear equations are these graphical objects, linear graphical objects, right? In two variables there, each equation is basically a line. So solving a system of equation is trying to find the point of intersection of those lines. Like this question is like, taking it down to the bare bones, right? What is it ultimately in terms of the graph? Okay. And that's what we're doing here, that raw work, and it looks like these two lines will intersect somewhere here, and that will be your solution, even based on my rough sketch. Now, to get your exact answer, you have to do this in a calculator graph or a graphing tool. You actually type in those lines going through those points, join those dots and then add a line through them and join other dots and add a line through them. To me, it looks like, uh, x value is 4 here because we marked it like the 1, 2, 3, 4, 5. And y value seems to be 1.9. Makes sense. Okay, this was 1 and that was 2 on the y-axis, right? So more or less, okay, not exact, more or less. Okay, 4 1 from me. Okay, and there is another problem for you to practice here. Let's do that. Okay, number 19 has an interesting concept. Find two different solutions of the given equation. Okay, and also give a general solution parameterized by x. So what does it mean? The concept is if you have only one equation in two variables, okay, now that is less number of equations than variables, right? That is the idea I want you to catch here. Number of equations, and in fact, actually, I should say something else. I should say number of independent equations, okay, because sometimes there can be a redundancy, I could give you 8x minus 10y equals negative 2 below it. And apparently, there are two equations, but it doesn't matter. Second equation is the same as the first, just multiplied by 2. Okay, it is not independent. By the way, that is another terminology to uh, catch here. In the language of all these linear equations, that is the word we use. Okay, dependent and independent. So in this case, these two are dependent. So now dependent. So one of them is dependent on the other. Choose whichever you want. Typically, we go with the one that has smallest coefficients, and that is your independent equation. Okay, all right. So the number of independent equations in the system. Okay, number of independent equations is less than number of variables. Less than the number of variables. When that happens, you will have infinitely many solutions. Okay. Number of independent equations is less than the number of variables. I'll write here. Okay. And actually, let me try to make that into a proper sentence. Okay. Number of independent equations is less than the number of variables. And the system is consistent. That is important. Okay. There is no contradiction. The system is consistent and number of equations is less than the number of variables. Whenever this happens, okay, whenever this happens, this leads to the conclusion is infinitely many solutions. Okay, mainly when the system is consistent and you have less equations than variables, what happens is to get a unique value for each variable, think you need at least as many equations as variables, right? If you want a unique value for x and y, at least two equations should be there, x equal to something and y equal to something. If you don't have two equations, how can you get a unique value for x and a unique value for y? Common sense idea, right? And this is something very useful. And that's what we have here. There is one equation, two variables. So infinitely many solutions. Only thing it says is among this list, identify which are the correct ones. And that is just plugging in. Okay, if you plug in 1 and 0, 4 minus 0 equals -1. No, the first one doesn't match. If you plug in the second, 6 and 5, 4 times 6 is 24, minus 5 times 5 is 25, equals -1. So the second option is true. Okay. The third option, 1 and 1, 4 times 1 minus 5 times 1 equals -1. That is also true. We'll come to D later. Let's look at E. That will be 4 times -1 minus 0 equals -1. Not true, right? So the first and fifth are not true. So B and D are particular solutions. Again, another word to catch here. There are so many terminology we are learning here, which is great. Okay. B and D are particular values of X and Y that work, right? There is no unique solution here. You have infinitely many, but doesn't mean random. See, infinitely many does not mean you can choose whatever you want for X and whatever you want for Y. It's not like that. You choose one of them, either X or Y. If you say the value of X is 6, the value of Y is 5 automatically. If you say the value of X is 1, the value of Y is 1 automatically. Okay. And like that, you can come up with pairs of numbers that work. Those will be called particular solutions. Now, how would you write a general solution? Okay. The general solution will be given in a parametric form here. Another terminology that you are introduced. Parameterized. Okay. What is parameterized? Parameterized is use one or more variables to express everything in terms of them. That is parameterization. Okay. In this case, instead of X and Y, just use X for to represent the whole solution. Okay. Everything in terms of X. So how can you get that? Very simple. Solve. Um, take that equation for, I'm sorry, use a pencil mode. Take that equation 4x minus 5y equals -1 and solve for y. What do you get? Negative 5y equals negative 4x -1. Move the 4x to the right side and divide both sides by -5. You get y equals 4 over 5x plus 1 over 5. When you divide by -5, no, the minus signs will cancel. 4 over 5x plus 1 over 5. And you can see that that's what is in option D. The y is replaced by 4 over x plus 4 over 5x plus 1 over. Okay. All right. We did many problems here. I will do one last problem, which is a word problem, and then I will ask you to practice any remaining problems in the document. Okay. In March, stock A rose from $21 to $22. Okay. Um, what that means is at the beginning of the month, the price per share. I hope you understand the language of economics. You should. Okay. If you are taking finite maths. And so I interpret. Okay. I'm not super into economics, but my basic understanding tells me that this means the share price of that per share was $21 at the beginning, became 22 at the end. Okay. Whereas the price of stock B dropped from 38 to 37 from beginning to end. Okay. Of that month. If you invested a total of 25,300 in these stocks in the beginning and sold them for that at the end, okay, how many shares of each stock did you buy? Interesting question, right? So you purchased a total of 20, worth 25,300 when at the beginning of March. And what was the prices then? $21 per share for stock A, $38 per share for stock B, right? So this data is in our mind. How do we like formally write it? In your written solution, okay, you begin like this, right? You say let. There is a sequence of steps we follow, which is first we let, I mean, we assign variables for the unknown quantities that you have to solve for, that the question is asking you to find. It is asking you to find how many stocks, shares of each stocks you buy. So you would say let the number of shares of stock A and stock B, number of shares of stock A and stock B purchased. B, okay, X and Y. We have two things here. Number of shares of stock A, number of shares of stock B. Okay, let them be X and Y. Don't forget to add the word respectively, otherwise it won't be correct. Right? So X numbers of shares of stock A, Y number of shares of stock B were purchased. And then you say by given. Okay. In the sense, what is given? What does the question give us? The question gives us you would have spent 21x dollars in purchasing the stock shares of stock A, right? Because each share was $21 and you purchased X of them. And similarly, you would have spent 38 Y dollars for stock B. And that would have costed you $25,300. All right? Think. And if you are beginning to understand, write the second equation based on the selling price when you sold them. Okay, and I'm sure you wrote it correctly. It will be 22x that you sold the stock A for, and 37y that you sold the total money from selling stocks shares of stock B, and that fetched you $25,100. Okay, this is the system of equations here. Now we have to solve this, and this is going to be a very interesting exercise. We will learn some skills here, very interesting skills. Be very focused. Okay, and also this is the last problem I'm doing in the video, so you can be relaxed and focused. The row operations. Okay, we are going to look at them through the perspective of row operations. The numbers, the coefficients that I see make me a little uncomfortable at the beginning because they're big numbers. What can I do? I can get the numbers become small. How? Adding and subtracting equations. This is one very important skill. Okay, so sometimes you might want to do just a couple of row operations just to reduce the size of the numbers, not particularly progressing towards getting zeros where you need and or eliminating the variables like for now. Okay, so what I mean is this. I'm simply going to do R2 minus R1 just so that the numbers will be smaller. Okay. Okay, by the way, that's your R1 and that's your R2. So when I do R2 minus R1, it's going to give me x, 22x minus 21x minus y, 37y minus 38y, you know, equals negative 200. Isn't that a better equation? Right? Okay. And I am now going to use that equation in with one of the like earlier rows and see, if that helps me um, get somewhere, cancel a variable. Okay. What could I do is this. I could first copy one of the rows. You can do this. Okay. You can sometimes simply copy a row back just to help you plan better. I'm simply bringing the first row back here. That was my R1, okay, that I brought here. Now, remember earlier we have done this work, so you ignore this now, okay? For your new state, that is R1 and that is R2 now, okay? So we're done with this. Now in this new R1 and R2, okay, how can I eliminate a variable? I will take the first row and multiply that with 21. Okay, you might wonder, we had 21x earlier, so why are we multiplying? Thing is, it's not the same row anymore. Be careful here. Okay, that new R1 is not the same as the old R1. Okay, now when I multiply with R1 21, that will be 21x minus 21y equals negative 4200. Okay, and then now if you see, just for like clarity, I could have copied this row again down here, but let me do it without copying. You will understand. We are at these two rows, okay, and I'm going to use those two equations to solve. Yeah, so I will still call this as my new R1 and I'll stay with my old R2, and now if you do R2 minus R1 in this new boxed system, okay, you cancel the 21x, right? And when you subtract, you change the sign. So 38 plus 21 will be 59y. Okay, equals 25,300 plus 4,200. That will be 29,500. Okay, and something tells me that I can solve this very easily, because y will be 29,500 divided by 59, and what comes to my mind is this table. Okay, 29 times 2 is 58, and if you take another 5.5, so 29.5 times 2 will be 59, right? So think looks like this will get perfectly cancelled here, and I'm going to get 0.5, because this is going to be half, reciprocal 0.5, but with 3 zeros, so that will make it 500. Ignore whatever I was talking. That was me doing mental calculation. You can punch this in a calculator. Okay, so 500. The value of y is 500. Let's go back and look at our options. Okay, I'm glad that there are two options which have 500 shares for stock B. Remember, Y is the number of shares of stock B. Okay. Now we need to decide, between B and C, which one is the number of stocks for share A, and that is the value of X. So we have not solved the system completely, right? We found the value of y, need to find the value of x. What could you do? You could do more row operations and manipulate, but I'm preferring to do the back substitution in any one of the previous equations. Remember, I don't have to go back to my first given equations. They have big numbers. I had this x minus y equals negative 200, a nice equation in between, right? Do substitution there. And this is, as I was saying, in this example, I'm going to talk about many skills. Okay. So this is another skill I want you to catch. Once you have the value of a variable, you can do back substitution. In fact, let me write the full word. That's called back substitution method. Okay. When you do the back substitution, you don't have to, you can basically choose from all the equations that you had um, that you had generated in between from start. Either one of the original equations if they are good, or any of the intermediate equations which has small coefficients so you can solve easily. Okay. Now when I do the back substitution, what do I get? I get x minus the value of y is 500 equals negative 200, and that gives me x equals 300. Okay, we add 500 to the other side, and which gives us option C. And that was the correct answer. Okay. I will just show you on the screen the other problems. Please solve them. The answer is given there. That is so that you can know that you have done it correctly. And this problem here. Okay. So in this document, you have got enough many problems to practice. Do that. Good luck. And I'll see you in the next lecture video for the next section. Thank you.